of the earlier videos, we already talked about vector and matrix norms. Basically, norm is a function which takes a vector, it could take a scalar as well, or a matrix, and then maps it into a set of real positive numbers. So it basically gives you a positive real number for every vector and matrix. So for such a function to be called a norm, there were some requirements, and well, several functions. Well, actually, you can define many different functions for that satisfies the properties of a norm, and you can use these functions whenever you need to measure, quantify your vector or matrix. When you want to assess the performance of a system, rather than measuring a vector at a constant time instead, or a constant vector, you are more interested in how the system behaves in a certain time interval. In that case, rather than taking the state vector and then measuring its norm, you take the state vector and watch it for a time interval, and you see how it behaves in that interval. In that case, you're interested in actually measuring a signal. So let's see how a signal is defined. Defined as a function from the time set into a set called the signal space. So this space can be a set of n-dimensional real numbers. So in that case, your signal takes time as the argument, input argument, which extends from 0 to positive infinity, and maps it into the set of n-dimensional real numbers. Okay, so we call this an n-dimensional signal, where it is indeed a vector, and every element of the vector is a scalar function of time, where the every element is a real number for each time instant. Okay, so for every time in that interval, each element takes a real value. So if this set is the set of real numbers only, then we call this a scalar signal. So for such a signal, p-norms can be used in a way similar to how we use them for for constant vectors. Well, actually, I would like to show you the analogy. So if whenever you have an n-dimensional real vector, this is what you have, right? I'm sorry, I think my pen is not working properly. Let me just, so x1 through xn, okay? And the norm for, the p-norm for that vector, remember how we defined it. So we defined it as the summation of the pth power of the absolute value of every element. So you sum them up through the entire vector, and you take the pth root of that summation. In the case of a signal, signal extends in the time direction. So rather than extending in the dimension of the vector, it extends in the time axis. So to make this more clear, so let's consider a discrete signal. Let's consider a discrete time signal, where your signal is defined as follows. Well, it starts from 0, and then it takes these discrete values, right? So x of t, x of 2t, and it goes all the way up to infinity. So if you wanted to define a p-norm for such a series, a discrete signal, then you could have defined the p-norm in a way very similar to how you define the norm of a constant vector, which would be take the summation of all these signals, x of it, and take the p power of the absolute values of those terms, and then take the pth root of the summation. If your signal is continuous time, then instead of summation, you will need to take the integral. Okay, so in the case for continuous time signal, continuous the p norm for a signal becomes the integral from 0 to infinity of the absolute value of the signal to the power p dt, and you take the p root of the integral. Okay, and this is already defined here. So this is how we define the p norm for a signal, for a scalar signal. And then we can discuss how these p norms are defined for that. Okay, in the case of a scalar signal, the signal extends from the positive real axis, time as the input argument, to the set of real numbers. And for p is equal to 2, the L2 norm of a real scalar signal is given in this expression. You take the square of the absolute value. Of course, when you take in the square, the absolute value becomes meaningless, so you don't have to put absolute value there. You take the square of the signal and integrate it from 0 to infinity, and you take the square root of the result, and that becomes the L2 norm of that signal. In the case of L1 norm, you integrate the absolute value of the signal in the interval from 0 to infinity. And in the case of L infinity, p is equal to infinity, the infinity norm becomes the supremum of the signal in the entire time from 0 to infinity. Okay, so these are the three major p norms that we normally use for a real scalar signal. This is what you have. You have an n-dimensional vector where every element in that vector is a scalar signal. So we know how to define the norms of scalar signals. So when it becomes a vector signal, how you describe the norm for that is as follows. So let's show this for the 2 norm. Okay, so in the case of 2 norm, you know how to calculate the 2 norm of every scalar signal. What you do is you calculate them, and then you calculate the vector norm as if you're calculating the 2 norm of a constant vector, which was given by this expression, right? So you take the norm of every element in that vector, you take the square of it, you add them up, and then you take the square root of the summation. And in that summation, every term is the signal norm of every element in that vector signal, which is given by this integral, and you have the square of them, right? So you just put the integral there. Now we can do the following trick. You have a summation, and inside the summation there's an integral. Okay, so and inside you have these xi terms, which both depend on I, which is the index for the summation, and depends on t, which is the integrand or the integration variable for the integral in between. Well, in mathematics, we know that if what you have inside is greater than or equal to 0, then in that case we can always change the order of summation and integration, which means you can put the summation inside and then leave the integral outside. Okay, so by switching the order of the summation and integral, the result doesn't change. So that we apply that trick here when defining the norm of the vector signal, and the 2 norm for that vector signal becomes as what you see here. And if you look at the inside, you have the summation of terms at a specific time instant t of your vector signal. And in fact, this can be written, this summation can be written in that form as the multiplication of x transpose at time instant t with x itself, which gives the scalar sum of these square of individual elements in that vector. Okay, and you perform this multiplication, then you integrate this term over time from 0 to infinity, and in the end you take the square root of that, and that gives you the 2 norm of your vector signal. Let's see how we handle them. A matrix signal is a function that maps time to a set of n by m dimensional real numbers. So at every time instant, a signal is a real matrix with a certain number of rows and columns, and every element in that is a function of is a scalar signal, in other words. So the norm for such a matrix signal is extended from the norm of vector signals. Basically, in the case of a real vector signal, we took the square sum of these elements in our vector. Now we extend that to include all the elements in the matrix. Okay, so that becomes a double sum. So we sum them through rows and columns. And in the summation, we have the two norms of these individual scalar signals, okay, which are expressed by this integral. And just like what we did in the real vector signal, we switch the places of the integration and the summations, and we're left with this double sum inside. And if you consider that double sum, it is equal to the trace of this product. Remember, x of t is a matrix. You take the transpose of that and multiply with the x of t itself. And then you take the trace of that resulting matrix, and that becomes equal to this double sum. Okay, so it's very easy to verify this fact. Okay, then you calculate that trace for every time instant. Then, well, the trace is a scalar, obviously. Then you take the integral of that resulting scalar term, which still depends on time, and then you take the square root of the resulting integral, and that gives you the two norm of a real matrix signal. Okay, and if you remember that this trace was in fact equal to the Frobenius norm of that matrix. So if you have a matrix signal, what you're doing is actually equal to finding the Frobenius norm for that vector matrix signal at every time instant, and then taking the integral of that in the entire time axis, and then taking the square root at the end. Okay, so now we have seen how we can find the norms of signals, whether they are scalar signals or vector or matrix signals. But these were all real signals, and this can be extended to complex signals as well. And in robust control, we also study norms of complex signals as well. And let's consider the following. So suppose that you have a real signal, and you take the Laplace transform of that, which gives you a complex function. Okay, so in fact, you can call that a complex signal, except that it's a function of s now, a complex variable, and not real time variable. So in that case, a complex signal is defined on the imaginary axis. We take the complex variable to be a purely imaginary number, which can be expressed as j times omega, and omega can extend from negative infinity to positive infinity. Okay, so a complex signal is a signal defined like that on the imaginary axis, which extends from minus j infinity to plus j infinity, and maps that into the set of complex numbers. Okay, so if this is just the set of C, then it is a complex scalar signal, and if it's a multidimensional term, then it becomes a vector or a matrix even signal. Okay, so for such a complex signal, we can define the L2 norm of the Laplace transform signal as follows. Since now our signal is a function of complex variable, or it's a function of omega, where omega is the variable for our purely imaginary input argument. Okay, so if you consider a complex plane where you have the real axis and imaginary axis, j omega is on the imaginary axis, and we're doing the integration from negative infinity all the way up to positive infinity. So we're integrating over the imaginary axis. Well, again, excuse my handwriting here, but I'm very uncomfortable writing on the screen of the laptop with my pen, and this is how I can draw them. So anyway, so the integration for the two norm becomes, as you see here, in the case of a real signal, taking the square of every term or the signal at a given time instant was not different than taking the square of the absolute value. But for the case of a complex signal, we need to maintain this absolute value sign, because now you have a complex number, right? And the complex number has two components, a real component and an imaginary component. So what you're doing is you have something like this, sigma times j times omega, something like that. And instead of taking the square of that directly, we take the length of that number. So your number is somewhere here. This is the real part and this is the imaginary part. We're taking this length of that complex number, and which is given by this. Okay. So instead of taking the square, what you do is you take this multiplication, and that will give you the xj omega, and this will give you the square of that length of that number. Okay, and you put that in the integral and perform the integration over variable omega from minus infinity to the plus infinity. And at the end, when you take the integral, you introduce a term 1 over 2 pi. Well, that's just a constant number. It doesn't really change the property of norm, but it is just introduced there for convenience. And for complex integrals, if you have studied complex calculus, you usually have that 1 over 2 pi or 1 over 2 pi j term. So this is just introduced for convenience. You don't need to worry about it at all. So, but this is how we can calculate the norm of a complex scalar complex signal. If you have a complex vector signal, then this is similar to how we handled real vector signals. Okay, so your complex vector signal is a vector where every element is a complex signal, and you calculate the two norm of that in exactly the same way as how we did it for real vector signals. You calculate the norms of individual elements in your vector signal, then you take the squares of them and add them up and take the square root of the resulting. You insert the complex vector signal norm for the scalar individual elements in your vector signal. Then you switch places of the summation and the integration, and this leaves you with this summation inside, which can be replaced by this product. Okay, and you take the transpose of this term, and this transpose of conjugate of x is usually denoted with star at the top. So I have mentioned this before, but in our future courses, perhaps you will see more often. And whenever you see a star on top of a capital letter, you should understand that that is a complex term. And putting a star there indicates you're taking the transpose of it and taking the complex conjugate at the same time. Okay, so this you integrate it from minus infinity to plus infinity on the imaginary axis, multiply it with 1 over 2 pi and take the square root at the end, and this gives you the two norm of your vector signal. And lastly, we have complex matrix signals, and there's no need to really go into too much detail about this. So this is exact repetition of what we did earlier for real signals. So you have a complex matrix signal, and the two norm of your matrix signal is given by this expression here. Okay, so now we have discussed how we can define norms of real and vector signals. And so let's come back here, and you have a system. Okay, and your system may have an input, let's call that r of t, and the output of your system is y of t, and you have a certain dynamics here, so which can be expressed either in terms of a transfer function h of s, and this will have a state space realization. So you can define the norm of your input signal, the norm of your output signal. You can do this in time domain, or you take the Laplace transformation of your input and output signals, which produces some complex signals. Okay, and you can calculate norms of your input and output signals as well in the complex domain. And then there's a system inside, in between, right? So you have a system in between, and how the norm of your output signal compares to norm of the input signal depends on what the system does to your signal, okay? So in that case, you cannot actually define a norm for your system. So rather than looking at the input signal norm and output signal norm, you can define a norm for the system itself, and that will tell you how the system will behave or what the system will do to the norm of your signal. So that's what we will discuss next as the system norms. But I would like to conclude this video here, and I would like to continue with the norms for systems in the next video. So I will talk to you in the next one.